Hi U12s, this is Mr. Lim here again, and this is our fifth video on volumetric analysis about primary and secondary standards. Okay, so we're going to learn about these two things. So, to get the known concentration of a substance, you can perform a titration from a primary standard to know the concentration of the solution. Okay, so you have a known, so you want to know what the concentration of a substance is. So what you need to do is you need to use a primary standard, which you already know the concentration of, to work out the other concentration of the other substance. All right, primary standard generally is a solution made up from a specific solid of a known mass to a specific volume in a volumetric flask so that the concentration is known to a high degree of precision. Okay, so the idea is you take a solid of some sort, you dissolve it, and it makes a solution. If that solid has a couple of specific properties, and if you make sure that that volume is very, very accurate, then you will have a very high degree of precision in your solution, and hopefully high degree of accuracy as well. Okay, so primary standards, what should they be? So they should, the solid this is, they should be stable, right? Which means that they don't react or decompose by themselves, okay? React with stuff in the atmosphere. They should be relatively easy to obtain, so they shouldn't be super hard to get. High degree of purity, which means that like if you have some 10 grams of it, you shouldn't expect much of it to be impurities. It should be, 9.99999 grams of the actual stuff. It should be relatively cheap, but that's not really too much of an issue. Should have known formula, so you should know what it is, and how it reacts with other things. And it should not absorb water from the atmosphere. Okay, so the idea is that if you leave it out for a little bit, you shouldn't expect the water from the atmosphere, the water vapor, to stick onto those solids and affect its weight and affect its concentration then. Okay, so that you only want the only mass that you ever measure is only of the solid. Okay, so most solids, they do not meet these standards. Okay, so these are very high standards, and not many things do. So substances that absorb water from the atmosphere, so remember that was one of the qualities that it shouldn't have. These substances that absorb water from the atmosphere are called hygroscopic, right? If a solid substance can absorb so much water that it can create a solution, okay, so in other words, it absorbs so much water it starts to dissolve in that water that it sucks up, it's called deliquescent. Okay, so hygroscopic means it absorbs water from the atmosphere. If it does it a lot, it's called deliquescent. Most common example of this is sodium hydroxide, where the sodium hydroxide pellets, if you leave them out in the atmosphere even for 5 minutes, what happens is that they absorb water from the atmosphere, and if you see them, they start to look wet and shiny because there's so much water being absorbed from the atmosphere. Okay, you leave it for long enough, it will actually form a very concentrated solution of sodium hydroxide because it'll keep on absorbing water from the atmosphere. Right. So sodium hydroxide, very common. So if you ever get a question about, why is sodium hydroxide not a very good standard, primary standard, because it's deliquescent, because it absorbs lots of water, or hygroscopic. Okay, some substances will react with substances in the air. Okay, so common things is that idea of that carbon dioxide is in the air, and carbon dioxide can form carbonic acid if it's ever allowed to dissolve in solution, and so therefore lots of bases can react with substances in the air and then aren't really stable and will change their composition. Okay, so not ideal to have things like that. Okay, so some common primary standards are your sodium carbonate decahydrate, okay, Na2CO3, that's the sodium carbonate, 10 water, deca meaning 10, and hydrate meaning water, or oxalic acid dihydrate, which is your oxalic acid, your H2C2O4, or this one, 2 water, or anhydrous sodium carbonate. Okay, so you can actually get anhydrous, which means there's no water on it, or hydrated sodium carbonate. All right, these three are the common primary standards that people will use. Okay, especially in acids and base situations. The waters in the hydrated substances are known to be in a specific ratio with the other compounds. Okay, so which means that if I have one, like for the sodium carbonate decahydrate, if I have 1 mole of sodium carbonate, I will always have 10 moles of water stuck on it. All right, and so therefore those extra waters, they give mass to the solid, and so therefore their mass is taken into account when creating a primary standard from these solids. Okay, so like if you want 1 mole of sodium carbonate, you will actually have to get 1 mole of sodium carbonate decahydrate if you're using the decahydrate, and take that extra waters into account. All right, so calculate the concentration of a primary standard with 2.45 grams of sodium carbonate decahydrate dissolved in 250 ml of water in a volumetric flask. So first of all, we know that the mass of our sodium carbonate 10 water is equal to 2.45 grams. Okay, we can work out the number of moles of sodium carbonate 10 water, which will be equal to 2.45 grams over its molar mass. The molar mass of sodium carbonate 10 decahydrate, okay, is, what is it? It is 286.15. If you don't know how to get that one, it is the sodiums, which is 22.99 times 2, plus your, don't forget the brackets, carbon dioxide, plus your 3 oxygens, plus 10 times 18.016, which happens to be the molar mass of water. Okay, which gets you then 8.56 times 10 to the negative 3 moles. Okay, so I have that many moles. I need to work out the concentration of this, but before I do that, I should really show that I understand that now, because I have the number of moles of sodium carbonate 10 decahydrate, I really want the number of moles of sodium carbonate, which will be equal to the number of moles of sodium carbonate 10 decahydrate. Okay, so therefore it would just be the same number, which is fine, but you should really show that you understand that you're only using this part of it to work out the solution, and then I can work out its concentration in 250 mils. C is equal to N on V, which will be equal to 8.56 times 10 to the negative 3 over 0.25, which is 0.034 mole per liter. Okay, so that's what I mean by taking the mass into account. Let's have a look at another question. Okay, oh look, the answer's there, don't look. Okay, calculate the mass of oxalic acid dihydrate that is required to make up 500 mils of that one there, okay, of oxalic acid. So the oxalic acid, I know the number of moles of oxalic acid, which is your HOOCCOOH, is equal to CV, because I'm starting with the actual solution, not the mass of the solid. Okay, so I go, okay, C 0.04 times 0.5, which will happen to be some value, 0.02, 0.02 mole. Okay, now I have to work out the number of moles of oxalic acid dihydrate, which will be equal to the number of moles of oxalic acid, because there's going to be a 1-to-1 mole ratio for those two things. So now I know I need 0.02 mole. Then I can work out the mass of this, from N times M, which happens to be 0.02 times, what value? 2 times the hydrogens, 4 times the oxygens, 2 times the carbons, and 2 times the waters, which would be 126.068, which will be then, 2.52 grams. Okay, so you take into account the water when working out the molar mass of anything, right? So let's move on. All equipment which is used in volumetric analysis has thinner portions where the measuring occurs. This gives the equipment ability to create a large meniscus so the volumes can be measured appropriately. That's why our pipettes have a skinny part here to create a large thing, as do our volumetric flasks, so that you can get a large meniscus to measure stuff properly. Okay, so to make sure that your primary standard solid gets into your volumetric flask, this is the process that you need to do to make a primary standard. So first of all, you weigh the solid in a clean, dry beaker, and you get the weight that you want to make the concentration that you want. All right. Then you dissolve the solid in a small portion of distilled water. Okay, so you pour in a bit of distilled water in there and it should dissolve. You can use a stirring rod if you have to. Then, using a funnel, you pour the solution into the volumetric flask, making sure you don't spill any, because as soon as you spill any, some of that solid is no longer in the volumetric flask and can no longer be put in there, and then you have to start all over again. So that's not great. So then, once you've poured it in, you use your distilled water bottle, okay, because that's what you're diluting it in. You rinse the beaker, because inevitably, there are going to be particles of that solid stuck on the inside of that beaker, which haven't drained into the volumetric flask. Okay, and so you rinse out the beaker to get out those leftover bits, and then you pour those rinsings into the volumetric flask. Okay, so effectively you're trying to get all of the solid, even the solid bits that were stuck onto the beaker, into the volumetric flask. You repeat this a few times to get all of the solid out of the volumetric flask. Okay, now if you think about it, where else can this solid be stuck? Right, where else could the solid be stuck that's not inside the volumetric flask? There could be some on the funnel. Okay, you do the same thing with the funnel. You rinse it through into the volumetric flask to make sure you get all of the solution in. And if you used a stirring rod, you should also do it with the stirring rod as well. Okay, because you want to try and get every little bit of this stuff that you just weighed into the volumetric flask. And that means rinsing everything thoroughly to get it all into the volumetric flask. Right. Then once you've filled it all, once you've rinsed all of the solid in there, you fill up the volumetric flask to the line. Okay. And that's that. You can shake it a bit and give it a bit of a good mix, but ideally you don't do anything to it after that. So if you go above the line, okay, so if you screw up and you put a bit too much water in there, you have to start all over again. Why? Because now it's no longer a known concentration, because you have no idea what the volume is, because you went over the line. And volumetric flasks do not have graduations like to say how much there is. There's only a single line. If you miss that line, that's it, done. Okay, so you do it all over again. So don't make sure you add that last little bit really carefully. Okay, so now you have your primary standard created, which is now a solution. You can use it to standardize, which means you find the concentration of another substance, okay, which is called a secondary standard because it's not got the same properties of a primary standard. Okay, why do you bother making secondary standards? It's generally because it's probably cheaper and easier to use than your primary standard, okay, because it might react in a different way to your primary standard, okay. Secondary standards are often unstable, that's why they're not primary standards, okay, or hygroscopic. And if you, that means that they're pretty good for the next couple of hours and most like a day or so, all right? So if you use it after a couple of days, then it's not going to be the same concentration. And remember, we're trying to get it to be a high degree of accuracy, so you don't want the concentration to change even a little bit. Okay, so it's only good for a couple of days, or at most, and so therefore you have to re-standardize it if you are really wanting to do this properly. And you should probably re-standardize it every time you want to do it properly if you really, really want to do it properly. All right, so that's it. This is primary and secondary standards. We'll be starting to do some calculations in the next video. Adios.